You thought it was sleazy that they didn't tell you what?
But they didn't tell you it wasn't Coca-Cola.
What was it?
Oh, wait, no, sorry.
Oh, that's number 2, the spring. The simple spring, I gotcha. Okay, I appreciate the use of the word sleazy, by the way. I never think of physics being sleazy, but that's cool. All right, so where we were at yesterday was we had gotten through A, B, and C. We had just calculated the angular momentum of the whole system. And everybody was okay up to there, yes? Okay, so part D, if I remember right, things ramp up a little bit. It says, while the system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned on the axis. So the idea is this little rod here is going to get pulled downward so that it ends up being like this, right? So the whole rod is getting pulled inward, okay? The same constant angular speed omega is maintained by the motor driving the platform. D says derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in the figure above. So the idea is basically you're pulling it. Originally the rod is pivoting about its end, right? And then the motor is going to pull it so it pivots about the center. Does that make sense? Okay. So when I first started to read this, I thought, oh, this is going to be a conservation of angular momentum problem, right? Because I was thinking, okay, well, there's, I erroneously, I've never used that word before, I wrongly was thinking that there are no external torques. So as you pull this thing in, it's like a figure skater pulling her arms in, right? Okay, what's wrong with that? Why is it not a conservation of angular momentum problem?
Same speed.
Good. The problem tells you that the motor maintains its constant angular velocity. Okay? So what that's telling you is there is an external torque. Okay? By the motor, exactly. Okay? And so that took me a second to process that the first time I read this problem. So that's an important thing to realize. Okay? So it says derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3 above. So the idea is now our radius has changed, right? As a result, our centripetal force is going to change and things get a little bit complicated, right? So, all right, so part D here is the deal. We know that our angular velocity is going to stay the same, right? Okay, so I think, how do I want to go about this? Or how do I want to go about explaining this? Is sort of what I'm stumbling on here. In the last time we solved this, we kind of started with this relationship here, right? Okay. So the issue is sort of both sides of this equation are going to change, right? Because as we pull it in, the radius of the circle that the object is following is changed, right? That's going to change the centripetal force, which therefore changes the force the spring needs to exert, which changes the amount that the spring stretches, right? Does that all make sense? Okay. All right, so let's see if we can come up with an expression for that centripetal force. Okay, and it's actually it's a very similar setup. We're going to start with this same jumping off point. Okay, so we want our centripetal force to equal the force by the spring. So our centripetal force is going to be m times omega squared times r, but we need to write an expression for r, right? Okay. So the issue is that my drawing is really crappy. That's the main issue. The issue is, so I know the length of the rod I've got is d over 2, right? I know right, but it's now pivoting at the middle, right? So the radial portion of the rod is d over 2, right? Okay. The unstretched length of the spring is d over 2, right? And then the spring is going to stretch some distance x, right? So I'm thinking that my radius is going to be d over 2 plus d over 2 plus x, the little bit that it stretches. Does that follow? Okay, so that's our goal, is to figure out what x is, okay? So, remember, centripetal force is m times omega squared times r, but we just decided that our r was d over 2 plus d over 2 is d, plus x. Follow? Okay. And that's got to equal the force from the spring, which is k times x. Make sense? Okay. So same jumping off point we had last time. So I think from there we just solve for, what are we trying to find? We're just trying to come up with an expression for x. What am I missing? The answer turns out to be d over 3. Oh, I know what I'm missing. I'm sorry. So we got to find a way to kind of simplify all this. Okay, so if you rearrange all of this and solve for x, I'm going to skip the algebra, but you can rearrange this, and you get x equals m times omega squared d all over k minus m omega squared. Everybody okay after there? Just some algebra. All right. So the issue is we need to simplify it further. This is a k. So I hate stopping halfway through a problem. Oh, I know. Okay. Yesterday, here's what I'm missing. Yesterday, we had figured out that k was 4 omega squared. That was the piece I was forgetting. Okay, so now what you can do is substitute 4 omega squared in, 4m omega squared, and then simplify that. So this is m omega squared d over k is 4 times m omega squared minus m times omega squared. Cool. And so you end up getting m omega squared d over 3 m omega squared, and you get d over 3. You simplify that. Good? All right, sorry. It's difficult stopping halfway through one of these problems. Okay, so that was D, and then E is the angular momentum of the entire system increasing, decreasing, or staying the same. What do you guys think? Okay, well, angular momentum is I times omega. There you go. Yep, omega is staying the same because of the motor. I is decreasing, so our angular momentum is decreasing. Follow? Okay. Then, in order to keep the system rotating with constant angular speed, is the motor doing positive work, negative work, or no work on the rotating system? All right. So remember, you guys, positive work equates to increasing the energy, right? And negative work equates to decreasing the energy. So are we gaining or losing energy? Losing energy, right? Because rotational kinetic energy, sorry, we used KR here, sorry, didn't we? That's 1/2 I times omega squared. Our I is the same. I'm sorry, our omega is the same, but our I is decreasing. So we're losing rotational kinetic energy, so the motor must be doing negative work to slow it down. Cool? Or not to slow it down, to decrease the rotational kinetic energy. Good? Okay, cool. Questions? Yes. Oh, you know, I didn't look it up. You can find it on the website. I think it's public. You can find that stuff. To me, this felt like, I mean, I don't know. It felt not horrible compared to some of the other ones I've seen. So I don't know if that's a good thing or a bad thing. But I don't know. Questions on it, you guys? All right. So I was processing this a little bit. So I think here's what I'm going to start doing. I am going to, on the days these are due, I think what I'm going to do is I'm going to pass out my written solutions to it along with the grading key, and then we'll do the Q&A on it the next day. That way you guys have some time to look stuff over, so it's not me going through every problem. I think that'll expedite things a little bit. Okay. All right. So anyway, that's a ways off. We've got to get through 13 and 15 yet. Okay, cool. Any questions on FRQ? All right, we got to change gears. Chapter 13 stuff. Why don't you dig that out? We are looking at a test on Tuesday, so that gives us a couple days to kind of get our ducks in a row. And make sure you guys are good on the 13 stuff. We answered a few questions on it one day last week. I think that was the day Mr. Amco was here. Which reminds me, I forgot to remind you guys yesterday about the extra credit. So get me the extra credit if you want. I told you that was due today, so you got till the end of the day to turn in that extra credit. Okay. If you don't remember what it was, I recorded the notes from it when Mr. Hamko was here on the 30th. It was the Thursday before break, is that right?
Something like that.
I think I mistakenly said Tuesday the other day, but it's Thursday. Okay, so get that in. I think only like 3 people have turned it in, so they are going to get a lot of extra. Okay, so what do we need to talk about here? Yeah, Ethan.
Pretty fun fact, 51 in the last section.
51 in the last section? Are you guys okay with just kind of jumping around?
Yeah.
Okay. Let's see, a satellite moving in an elliptical orbit. That one? All right, let's see, what do we got? Oh, wow, that's funny. My notebook is open to that very page. All right, let's see. A satellite moving in an elliptical orbit is 360 kilometers above the Earth's surface. Why did I say that in stressing terms? Yeah, because remember, all the equations deal with r, which is measured from the center of the Earth. Okay, so just make sure you're aware of that. All right, so here we go. Number 51 from whatever, chapter 13. So here's what I know. Here's that. Here's my satellite. I know that this distance is 360 kilometers. I'm just going to go ahead and tack on 3 zeros and make that meters. Let's see, it's at its farthest point, and then it's only 180 kilometers at its closest point. So that's 180,000 meters at its closest point. Okay, cool. Calculate the semi-major axis and the eccentricity of the orbit. Okay, so first of all, does the drawing make sense? Okay, so here's my ellipse. Here's one of my focal points, and then the other one is somewhere over here. Actually, it's probably going to be in the Earth because these distances are small compared to the size of the Earth, so maybe something like that. Cool. All right. So A says to calculate the semi-major axis. So can you just describe to me what we're trying to find there, Ethan? Yep. Yeah, exactly. It's half of the largest one. So I need to take that, find that distance, and then chop it in half. So it's basically 3,600 meters plus 1,800 meters plus the diameter of the Earth, and then chop it in half.
Yeah, I did that and I kept getting 657.
Oops, this is the wrong sheet. Oh, it also clearly can't be in kilograms. Yeah, I think we talked about that the other day. Well, so here's the radius of the Earth. I guess I did all my calculations in, well, whatever. Okay. So the radius of the Earth is 638, 1, 2, 3, 4, yeah, meters. Good. So if you double that, that means that the diameter is, oh, I didn't do it that way. Yeah, I don't know. What did you say you got?
I got 6570, but then again, I didn't know. I put 6.3%.
Gotcha. So that's probably the difference. Yeah. And actually, for some reason, I had 6. The problem, you guys, is depending on the source you get, we need to just come up with a standard for this. I have 6.37 here. For some reason, the book used 6.37 times 10 to the 6th. But everywhere else, I've seen 6.38. So anyway, it sounds like you're in the neighborhood. You got the right idea. So that's the important thing. Okay. And then once you've got your eccentricity, remember your eccentricity is, F over A. So A is your semi-major axis. That's what we were just talking about. And then F is half of the distance between your foci, right? I really should look up whether it's focal points or foci. Is it foci? I always get it mixed up because it's focal points with optics, and I always get them mixed up. So we need to find our F. So let's see. We know our semi-major axis. We can easily find this distance, right? So your F is going to be the difference between those two, right? So F, if you figure it out, ends up being 90 kilometers.
Wait, so F is from the center of the ellipse to one focal point?
Correct.
Okay.
Yeah, everything is half of what you would expect to be. So anyway, those are the numbers I have. All right, Tiffany, okay?
So 6.37 is what we're going to lose.
You know what, on the test, I'll make sure I give it to you, so there's no confusion. And I just need to, I'll sort that out. Okay, are we good? Okay. And the AP sheet, when you get it, has a list of constants. I wonder if it has the mass of the Earth on there. It's not, really? You are right. Okay. Well, they'd have to give you that. Oh, but they give you the acceleration of gravity at the Earth's surface. Like you don't know that. Huh. Okay. All right. Anyway, we good? What else? Yeah. 23 from 13.3. One model for a certain planet, that one. Okie dokie. Is that going with a little drawing here? No. Okay. All right. One model for a certain planet has a core of radius r and mass m surrounded by an outer shell of inner radius r, outer radius 2r, and mass 4m. Got it. That took some reading. All right, so one model for a certain planet has a core. That means like the center part of the planet, right? So here's our core. We'll draw that in black. It's got a radius of r and a mass of capital M. And then it's got surrounded by an outer shell of inner radius r and outer radius 2r. Basically, they're just implying that there's no hollow space there in the middle. And it's got a mass of 4m. There's our drawing. And then it says that m is 4.1 times 10 to the 24th kilograms. And it tells us that r is 6 million meters. And it wants to know the gravitational acceleration of a particle at points r from the center of the planet, got it, and 3r from the center of the planet. Okay, so for part A, I'm looking for the acceleration of gravity here, right? Okay. So a couple quick comments. First of all, this is basically a shell theorem problem. Do you guys understand that? Because, like, you know, all of this is kind of uniform, and then all of the blue is kind of uniform, right? Now, at this red point, what is the force of gravity due to the outer shell going to be?
0.
Does anybody not understand why that's true? Right? Because remember, anytime you're inside of a shell, the force of gravity from that shell is 0. Good? All right? So that means that the force of gravity at that red dot there is going to be just because of this, right? So my force of gravity there is just going to be g times m times little m over r squared, right? Which means that my acceleration of gravity there, I'm going to just divide by m, right? And you get g m over r squared, right? Does that make sense? And then you can plug in the numbers and see what you get. But are you okay with that? Okay. And then for part B, what color are we going to use? Green. Part B, it wants to know what the acceleration of gravity is going to be a distance of 3r away. So now you just need to take into account the entire mass, the mass of the whole thing. Because since this is a sphere, you can treat it as a particle point located here. Follow? So now your force of gravity is going to be G times, let's see, what's my total mass? M plus 4m is 5m times the mass of the object over 3r quantity squared. And therefore your acceleration of gravity is going to be the same thing without the little m. Oops, that's the worst A in the history of A's. There is. There's a YouTube channel. Check it out, historyofa's.com. Say that again?
Sounds subtle laugh.
We'll work up to it, I gotcha.
Yeah.
All right, are we good? Does this make sense, Francis?
Yeah, it's just a picture. It was kind of like.
I gotcha. Yeah, a lot of that was just interpreting the wording. Jake, yeah.
So is 4m just the mass of the shell? It's
Correct. That was the way I interpreted it. Yeah. Surrounded by an outer shell with a mass of 4m. Correct. Bless you. Twice. Not going for a third though. So. All right. Everybody good? Questions? All right. What else do we need to talk about? That shell theorem is important, you guys. Yeah, shoot. No, I'm glad somebody's asking questions.
12, 13.
Say that again?
It's going with that.
Oh, number 12? Oh, yeah. All right, let's see. What do we got? Number 12 from chapter 13. In graph, particle A is fixed in place at x equals -2. So here we go. Well, let's make ourselves a little drawing just so we have a frame of reference. So here we go. Here's B. Here's A. X equals -0.2. All right. Particle B, so let's see. So the position of A is -0.2 meters. The mass of B is 1 kilogram. It's fixed in place at the origin. Particle C, not shown, can be moved along the x-axis between particle B and x equals infinity. So particle C is going to go here somewhere. And we just got to figure out where it goes, I believe. Graph B shows the x component, F net in the x direction of the net gravitational force on particle B due to particles A and C as a function of the position of particle C. Okay, so, holy cats. So here's our graph. So this represents our position in meters. This force over here is the force on particle B. So I'm going to put a little b there just so that we understand that that's the net force on object B. Yeah, it says on particle B due to particles A and C. I know, that threw me off too the first time I read it. So here's our graph. So this is 0.4 meters. All right. The plot actually extends to the right, approaching an asymptote. You guys okay with the word asymptote? What does that mean? Yeah, it's like so it's going to approach that line, and it tells us that that asymptote is at -4.17 times 10 to the -10th newtons as x goes to infinity. So what are the masses of particles A and C? All right, so two unknowns, right? We need the mass of A and the mass of C. Two unknowns, what should I be thinking? Two equations, right? System of equations. All right, so let's interpret the graph for a minute. Before we get into solving, let's make sure you guys understand the graph. What is this telling me? The fact that as my x goes to 0, my force is going to infinity, Talk to me about that. Why is that true, or what's going on there? Yeah, the idea is as object C gets very, very close to object B, the force of gravity is going to go to infinity, right? As you get infinitely closer to an object, as your R goes to 0, your force goes to infinity, right? Okay? So that, I don't know that that point helps me any. But I see 2 points that I feel like should help me. I feel like this point right here ought to be helpful. What's that point telling me? Good. It's telling me that the net force when your radius is 0.4, or when your position, I guess I should say, is 0.4, it's telling me that the net force is 0, right? So that means that blue point is telling me that if I calculate the force of gravity between A and B and the force of gravity between C and B at x equals 0.4, I ought to get 0, right? So that's going to be my first equation. So let's write out what that equation looks like. So this force is going to be G times the mass of A, times the mass of B, which I know that's just 1 kilogram, so I'm just going to leave that out, over, let's see, the distance from A to B is, oh, well, that's just 0.2, right? Cool? And then one of those forces has to be negative, right? So I'm just going to make this minus G times, let's see. So now we're talking about the force between B and C. So that's the mass of C, which I don't know, times the mass of B, which is 1 kilogram, over 0.4 squared. So there's equation number 1. Follow? Okay, so, and you could simplify this. You could certainly divide out the G's, right, to simplify it. Okay? Now, the other point is attained by thinking about that asymptote. Okay? So, how does that work? Refresh my memory here. What's this, number 12? So when you're at infinity, oh, right. Sorry, I was thinking we're looking at C. Okay. So at infinity, here's what I know. I know that the force between A and B plus the force between C and B has got to be negative 4.17 times 10 to the negative 10th newtons. Okay? But remember, this represents the position of particle C. So if C is at infinity, then this goes away. Right? Ah. Oh, well that means then that G times the mass of A times the mass of B over 0.2 meters squared has got to equal that number. Oh, well that lets me solve for the mass of A right away. And then once you got the mass of A, you can find the mass of C. Make sense? So sometimes, even though this was quote-unquote a system of equations, one of the systems was very easy to solve, right? So this allowed us to find the mass of A, and then you plug the mass of A in over here and find the mass of C. Is that enough, or do you guys want me to run through the algebra?
Yep.
Okay, cool. Those graph problems are huge, you guys. I see them all over the AP test, and it's about what are the important points in the graph that are going to give me the information that I need to solve the problem. Okay? And do you guys understand why I focused on that blue point and the red point, the asymptote? Okay. What else? Did you ask about another one too, Francis? Did you say 13, or were you just saying 12 from 13? Okay. What else you guys got? Yeah. 16? How did I lose the page that quick? I'm looking at it. Holy cats. Oh, the integral one. Yeah, Francis, we were talking about this one the other day. Did you end up figuring it out? Cool. All right. Yeah, this one, I'm glad you asked about this one, because it's one of those things that like if you look at the standards on the AP thing, it says students should know how to solve problems like this. Go ahead. I can't imagine them giving you anything more complicated than this. And then more easier than this, then there's no integrals and it's just using the equation, right? So honestly, I think the odds of them giving you a problem like this are slim when there's so much content to be covered. I think that this is probably not something they would stress. And technically it's something that is in the, you know, the curriculum that we're supposed to do. So I felt like I should give you one and we'll run through it. I would be really, really surprised if it was on the test. Okay? I'm not saying it won't be, because it is in the curriculum, but. All right, so it says in the figure at the right, a particle of mass m equals 0.67 kilograms is a distance of 23 centimeters from one end of a uniform rod with length of 3 meters. So let's make ourselves a little drawing. So we've got this little red ball here. We will call that m1. We know that it is 0.67 kilograms. And then it's placed a distance of 0.23 meters from this rod of uniform length of 3 meters and capital M mass of 5 kilograms. What's the magnitude of the gravitational force? Blah, 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 blah. Okay, so when I first sat down to do this, I just sort of jumped into it and I was like, oh, well, that's easy. I just find the center of gravity and find the force of gravitational attraction between the center and here. But it doesn't work. Okay? And the reason for that is because of the r squared issue. Basically, what ends up happening is that, how do I want to say this? Let me think about why the r squared affects us. I think going through the math will show us a little bit. But basically what it boils down to is that the impact of this is, like, if you've got a point that's twice as far away, it's going to have more than twice the impact. Did I say that right? Or I think I said it wrong, but I think you know what I'm trying to say. And it's because of that r squared. Okay? So what you need to do is you need to imagine looking at a little chunk of, you know, sort of infinitely small size, you know, very small chunk, and finding the force of gravity due to that little chunk and then summing them up, right? Oh, but that just means integrating, right? Okay? So what we want to do is we want to calculate the force of gravitational attraction. So that is going to be the sum of g times, let's call this little chunk here dm. Okay, so m1 times dm over the distance to that guy squared, right? Follow? Yes. To explain that, I'd have to go through the shell theorem. Like the proof of the shell theorem, and you guys don't want me to do that.
All right.
And to be honest, I'd have to look it up. It's been a little while since I've looked at it.
So we can only take sphere and center everything else through this.
Yes. Yeah, did you guys hear that? I think that's maybe something that I've not stressed as well as I should have. Okay, the only thing you can treat as a point particle is a sphere. Or something that is very, very small compared to the distance. Good? Okay. So we need to rewrite this then as an integral. So this is the integral of g times m1 dm over r squared. And I need to integrate according to mass. So the boundaries of my mass are, I'm going to integrate from a mass of 0 up to the total mass of the bar, which is 5 kilograms. Cool? All right, but the problem is, and this is huge, you guys, you need to understand this trick. I've seen this on a bunch of things. The problem is, I can't integrate according to little m, because little m doesn't show up in this equation. This m1 isn't the same as little m, right? That m1 is this mass. whereas little m sort of represents the kind of the mass of the bar. All right, so I need to come up with another relationship. All right, now the bar is uniform. Why is the fact that the bar is uniform important, guys?
Equivalent, like in each spot.
Good. Each little chunk has the same density, right? Each little chunk of the same size is going to have the same mass. So that means that if I do this, if I do dm over dr, in other words, if I take a little chunk of mass and divide it by a little change in radius, that's the same as the density of the whole bar, which is 5 over 3. And therefore, dm is just 5/3 of dr. Follow? So, I can rewrite that integral then as the integral of g times m1, and I'm going to replace dm with 5/3 dr. So I'm going to put the 5/3 out here, put the dr here, divided by r squared. Yeah, Ethan?
So when dm over dr equals m over l, it's like going to show up a lot.
Yeah, and so you have to use that trick a bunch when you're calculating center of mass.
Is it the only trick it's going to be used with manifolds?
There is, we need to go back and do some of those air resistance problems. I don't know if you remember me talking about those problems where the air resistance changes. That has a similar trick, and I'll make sure we hit one of those before the test. I'm gonna, not that this helps you guys any, but I'm going to try to make a list of those things so that next year I can stress them. All right, so are we okay up to here? Up to here? We okay up to here. All right. So is my integral still between 0 and 5? No. Now I'm integrating with respect to my radius, right? So at what radius does my mass equal 0? 0.23, right? And then I need to integrate from 0.23 all the way up to 3.23. And then from there it's, just an integral. All right. So what number is this? This is 16. I'm going to jump ahead here. You know what? Let's just do it. So I don't know if you guys are like me. I hate whenever this looks like a fraction. So I would rewrite this as r to the -2, and then integrate that. Okay. And so you're going to get, let's see, 5/3 times. Let's see. What are we going to need? We're going to need a -1/3 to get rid of the 3. G m1 r to the -3. Is that right?
It's -1.
Oh, -1. Right. Sorry, I went the wrong way. Oh no. -1, -1. That'll work. Yeah. Cool. And then between 0.23 and 3.23. There we go. Cool. And then plug in your numbers and solve it. Cool? Cool. Let me just make sure. What, that's 16. Yep. Okay. Cool. All right. I think we probably have time to do one more. I need to. Let me ask Mr. Pata about what the restrictions are on calculator use. Let me shoot him an email. So what are the things I need to ask about? You guys were asking about this the other day. So I need to ask about if you can use regression. With like 99% confidence, I can say that sig figs should not be an issue. Regression, and then doing calculus. graphs and that kind of stuff. Yeah. Okay. Anything else you guys can think of calculator-wise? Or otherwise, I guess? The last time I asked
There's a
this.
simplifying question yesterday.
Oh, right. That's one where I would go, just do it. But okay, cool. I'll shoot him an email and we'll see.
He said that as long as you get in terms of the variables they want, you can number to simplify it. Especially if you're like putting it in a certain formula, you can make the problem more likely to be wrong. Like you can make mistakes along the way putting that forward.
Right. Gotcha.
When it comes to telling answers.
Okay, what else, you guys? How are we feeling about this stuff? Is the lack of questions because we're just not done with the work yet, or is it we're pretty good with it? What's that? A little bit to do? Okay. All right, so over the weekend, you guys finish up whatever you haven't done. Monday, we've got a short period, but I'll answer questions. I'm figuring, whatever, between 12 and 15 multiple choicey questions and one kind of FRQE kind of question. I think that hopefully I would think that the questions are fairly predictable, right? It's, things that and I haven't started writing the test yet, but things that jump to my mind are shell theorem, right? Escape velocity, circular velocity, making sure you understand the relationship between gravitational potential energy and kinetic energy of an object in orbit, circular or otherwise. Most of what we did today was spent focusing on force of gravity, so maybe on Monday we'll try to focus more on the energy stuff. We can do any energy problems today. We'll make sure we hit some of that on Monday. Kepler, thank you. Yep. Remember, you guys, Kepler's third law is basically the same as you can very easily derive Kepler's third law by using basically Newton's laws, right? If you rewrite centrifugal force and set that equal to the universal gravitation equation, you can pretty easily derive Kepler's third law. So I'd make sure you know to do that. There's also those two FRQs that are at the back of the packet. At some point, we should go over those.